All right, everyone, good morning. Wherever you are, whoever you are, however you are, thanks for joining us for today's webinar, 3D Circuitry on Thermoplastics. Today we're going to be taking a look at creating molded interconnect devices with laser direct structuring. A little bit about us. We are LPKF Laser and Electronics. We manufacture laser systems, and we are the patent holder for the laser direct structuring process. My name's Shane. I'm in the marketing department here just outside of Portland, Oregon, and I'm joined today by Stefan Schmidt, president of LPKF North America. Thanks for joining us today, Stefan.
Yeah, hey, thanks for putting this together, Shane.
And Don Porter, global account manager who works extensively with the LDS process. Don.
Good morning, Shane.
Thanks, Don. If you have any questions throughout today's presentation, go ahead and submit them via your GoToWebinar questions panel, which probably popped up on the right side of your screen, or you can submit your question via Twitter. Our Twitter account is at LPKF_USA. As always, 1,000 bonus points to anyone who submits their question via Twitter. So what's on slate for today's presentation? Well, we're going to talk a little bit about the rise, fall, and subsequent rise of the molded interconnect device. We're going to follow this up by talking about how you make MIDs, and then we're really going to dive into the laser direct structuring process. We'll follow this up with an application section, and then finish off with some next steps. But first, let's talk about just what a molded interconnect device, or MID, is. Basically, what a molded interconnect device is a part that combines all mechanical and electrical functions into a single part. So in the case of what we see here on the screen, basically you have a circuit board, a housing, a connector, and a cable all into one part. Now, as you can imagine, putting all these parts together into a 3D environment like this has a lot of advantages. The biggest thing, as we mentioned, in putting all those parts together, you have fewer components and fewer parts, so there's less complexity of the overall part design. Now, by reducing those components, you save a lot of space, you reduce the weight of your part, and it really lowers the overall cost of production. And then the other great thing about the MIDs is that when you are working with a 3D design workspace, this really opens up design possibilities. It allows you to bring together your best minds, your best mechanical engineering minds and your best electrical engineering minds, and really tinker with new possibilities. A little bit about the history of MIDs. So MIDs, like myself, Magic Johnson, cassette tapes, and the NES, broke onto the scene in the 1980s. Now, there was a lot of buzz about MIDs and a lot of trade magazines and other industry sources, but despite the early fanfare, they didn't really catch on. Now, why was this? Well, there was kind of a high threshold for entry into the world of MIDs. There was not a lot of flexibility for mixed manufacturing environments, so if you wanted to dive into this new technology, you had to do it with large quantities without much room for prototyping or R&D beforehand. And anytime there's a new technology, people want to experiment with it first. So because of this, the buzz for MIDs kind of died off. However, in the last decade or so, demand for MIDs has really picked up. Now, why is this? Well, as we all know, products are getting smaller. This trend of miniaturization is really forcing designers' hands when it comes to finding innovative ways to design their products. And then finally, there have been some new manufacturing methods which have really sort of lowered that threshold into the world of entry for MIDs. All right, I need a breath, so I'm going to bring in our panel here for the first time today. I wanted to ask them what they think is kind of the most important feature about MIDs. I'm going to start with Stefan. Go ahead.
Yeah, so one of the things that I think is really, really important about MIDs is really the use of a three-dimensional workspace. Being able to use a plastic component outside of the circuit board to really use it for real estate, for circuitry, makes a big difference in the overall part design. Now, if you think about it, most, or basically all circuit structures, rigid boards or even flex boards, they start their life as a two-dimensional circuit. And to break the shackles of the two dimensions, you really have to come up with something else. And that's really where MID comes into play. So you really start to create a circuitry that, so to speak, goes up the walls and uses all the space around it.
Gotcha. And then, Don, what do you think is kind of the most important feature about MIDs?
Well, to get value out of an MID, you really need to reduce the components in your part. I mean, you're taking the basically the structure or the housing of the part, you're putting the circuitry directly on it. So you're taking out a PC board or a flex circuit or a wiring harness. You're reducing the complexity of manufacture, the complexity of assembly, and you're reducing manufacturing steps. And this should increase your quality rate and make your overall production process a little bit less expensive and a little bit less complicated.
Gotcha. All right, so then talking about kind of the benefits of MIDs, we get into what are some MID manufacturing methods. So go ahead and, Stefan, why don't you explain kind of some of the MIDs, some ways you can make an MID?
Yeah, so Shane, initially you mentioned, again, the rise, the fall, and the rise of MIDs again. Let's talk a little bit about the rise and the fall in the first part of that. MID really broke the scene with a process called two-shot molding. Two-shot molding is a process where two different types of plastics are being injected into a fairly complex injection molding tool. So one for the circuit feature and one for the housing or the mechanical carrier feature. Now you can imagine this is fairly complicated and really cost intensive, and this makes it really hard to come up with complex designs or change designs because everything is part of the molding part. So the process is kind of like a toothbrush that's made out of two different plastic parts. So that's kind of how you can imagine this, and it's using one part of plastic that's platable and one part that's non-platable. So again, the circuitry is really a function of the molding part itself or the molding tool itself. Now, again, this is where kind of the fall of the LDS part came into play. This is a very efficient technology for very large, for large parts, for very high volume parts, and for fairly simple parts. However, when parts become more complex or quantities are smaller, then all of a sudden we run into a lot of cost constraints or technology constraints with that. And that's really, what made, LDS, what limited MIDs in the past. Now, the LDS technology, the laser direct structuring technology, really broke this limitation there by separating the circuit function from the injection molding. It basically just injection mold a single shot plastic part and then add the circuitry on it later through a laser process, basically a data projection on the part itself. And that gives us a lot more flexibility, both in small quantities and prototypes, as well as in mass production, and also leaves us some room for tweaking even parts in mass production.
Gotcha. Thanks for running over those basic benefits. So now, like I mentioned, this is webinar's 3D circuitry on thermoplastics with a focus on laser direct structuring. So now I'd like to kind of expand where Stefan came off of and get into the LDS process. So what is laser direct structuring, or as it's known by shorthand, LDS? Well, it's a three-step physiochemical process for creating 3D circuitry on molded interconnect devices. And the three steps in the LDS process are injection molding, laser activation, and selective metallization. So the first step, as I just mentioned, is injection molding. Now, kind of what makes LDS different at its fundamental base level from, say, two-shot molding of molded interconnect devices is that you're using a one-shot injection molding process of doped thermoplastics. So Don, why don't you come in and talk to us a little bit about kind of one-shot molding versus two-shot molding and a little bit about those doped thermoplastic materials.
Well, Stefan brought up two-shot molding, and this is where you're flowing two types of plastic into a complicated mold with your circuitry is basically developed within the mold. And those two types of plastic, one is conductive and one is non-conductive. Now, the beauty of the LDS process is you just use a single shot, a fairly simple mold. If you can imagine, like a little green army man from when you were a kid. So it's a very, very basic mold. But you're putting a plastic in there that's non-conductive, but it has a dopant that can be laser activated to be conductive. So your structure, your conductive structure, is then put on with the laser later. Now, these grades are available from all the major plastics manufacturers in all major grades of plastic, from polypropylenes to PCABSs to nylons to LCPs. So there's quite a wide variety that you can use in the design process.
Gotcha. And then going along sort of with this one-shot molding process and kind of the separation of the two different, one platable part and one non-platable part into one part, I know that has a large effect on sort of like the design freeze process. So maybe you could talk a little bit about that?
Well, another thing that Stefan brought up was the kind of the large number of parts that two-shot molding required to be profitable. The other thing that it needed was kind of a long design process where you maybe made the same part for several years. Now we all know that doesn't happen so much these days, that parts turn over very quickly. So the beauty of LDS is that you can design, you can have your mold built, you can freeze the design way past that point. In two-shot you have to freeze the design before you build your mold. So you can freeze the design way past the point of the mold. You can tweak the design after that. So your design freeze can be much later, and the ramp up to full production, to fairly high quantity production, can be fast. So short lifespan products can be run very well with LDS process.
Awesome. Thanks for explaining that, Don. So as we go through the 3 steps of the laser direct structuring process, I kind of wanted to create an MID with the LDS process. So the result of our one-shot injection molding phase is this part you can see here on the screen. So the granulate has been formed for this part, and we'll find out what it is when we're done with the 3 steps. But once we have this part, it's time for the next step of the LDS process, which is laser activation. So here, this is a physiochemical reaction where the laser etches the wiring pattern onto the plastic and prepares the part for selective metallization. And to dig a little deeper into this, I'm going to go ahead and bring in Stefan.
Yeah, thanks for the transition here. We actually do dig a little deeper now. We really go into the plastic material itself and see what's happening on the inside. So here on the screen you see a representation of the plastics matrix here, the plastics material, and then there is a catalyst compounded into the material, here represented through those green and blue dots. The green dots are metal parts, metal atoms, and they're packaged in an organic packaging. And this catalyst, this metal-organic complex, is compounded throughout the plastic material. And you see this in the picture on the upper right side. There's like this yellow block, like the cheese block there for the plastic material, and all the black dots in there representing the catalyst compounded throughout the material. Now, once we hit this part with the laser, then all of a sudden the magic, the LDS magic happens here. We separate the organic packaging away from the metal atoms and all of a sudden expose those metal atoms. Now that has multiple effects, and one really important one is now we have something that can receive a selective plating only in those areas where we actually have activated with the laser. So all the other catalyst atoms or molecules, they stay completely inactive, and only those particular ones that we hit with the laser became platable right now. And that's represented in this picture right now, where you see those little green dots on the surface which represent the activated catalyst parts versus all the black dots that are still throughout the plastic material as a non-active.
Gotcha. So moving up from that molecular level and onto the surface of the part, here you can see kind of what an MID that's been hit with an LDS laser looks like. So Don, why don't you kind of explain to us what we're looking at, kind of beginning with that smooth surface on the right.
Well, the smooth surface on the right is just the basic plastic molded surface, and you can put plating on this. We've all seen cosmetic plating done on maybe like a lipstick container lid, and you know that you can scratch that and peel that right off. It has very, very little peel strength, but it's just cosmetic, so they're not too concerned about it. We're very concerned about the peel strength in our product, and so aside from activating the dopant in the plastic, the other thing that the laser does is it roughens the surface. And you can see there on the left a very rough surface. And this gives us very good adhesion to the surface with the plating and a very high peel strength.
Gotcha. Thanks, Don. And then I actually just saw one question come in. Someone who came in late and asked what MID stands for. So for anyone who came in late and you don't know what MID stands for, it stands for Molded Interconnect Device. Basically a 3D part that combines the connectors, the housing, and the wiring all into one 3D part. So going back, we started at the molecular level of the laser activation process, moved up to the surface of the part, and now we're going to take out one step further into an actual LDS system to kind of see what happens when the laser hit the parts. So Stefan, why don't you describe to us what we're about to see in the animation?
Yeah, so here on the screen you see, before we roll the tape on this, you see a representation of what the inside of one of those LDS machines looks like, laser direct structuring machines. So here, represented through multiple different colors, we have various different lasers that hit a part all at the same time. So we really start to wrap the circuitry around it simultaneously around this entire part. So this is a high-value manufacturing machine that we see here. And if Shane, if he rolls the tape right now, then you probably start to see the animation happening on your screen. So we have 4 different type of lasers that are operating. There are 3 on the surface there, 1 coming up from underneath, and now we are structuring on the part. While one part is loaded, we are putting a circuit structure on the other, and then the laser flips around and works on the other part. So again, these are very, very high throughput machines producing high quantity consumer electronic device parts right now. So you can see that LDS technology, although it's a serial process, is not only for high mix and small quantity, but it's also very, very competitive for very, very high volume, low price parts.
Gotcha. And then those 4 laser colors, those are just figurative, right?
Exactly. They're not different color lasers. It would be nice, but it's all invisible light lasers. So of course, we only have different colors, so we can represent a little bit what the different lasers do. So
sadly, Star Wars, this is not. But it is an MID that has been hit with a laser, as you can see here on this slide. So the gray areas that you can see on this part are the part that were hit with the laser, kind of that roughed up surface that Don talked to us. So the final step in the LDS process is metallization, and specifically selective metallization. So basically what you have here is an electroless copper plating. And what's interesting about this, so once the ions, the chemical ions, or say the copper ions in the solution, when you submerge the part in the solution, they kind of go over and they attach themselves onto that roughed up surface, that laser activated surface, and then you have metallization. So here you can see a cross section of a metallization. Again, this is down at the very molecular level, which is why you can see all the little variations in it. But Stefan, why don't you walk us through this metallization we see on the screen?
Yeah, so here on the picture, on the left side of the picture, we have a cross section through a plastic part with the circuit structure on top of this. Down in the you see those white spots in the black area. Those are representing the mineral fill or glass fill of an injection molded plastic material, and then you can see the circuit structure laying on top of that. Now in the close-up picture on the right side, you see the cross section in more closely, and you see this almost like this ocean-like surface there. And that's really the micro edge surface that Don talked about earlier, which really allows us this wonderful peel strength of the material, where the copper really grows into those little cavities in the material and leaves a phenomenal peel strength behind. So typical buildup is we always start up with an electroless copper. In this case, it's a 5 micron copper, but it could typically be bigger. In most applications, we see 8 to 10 up to 12 micron copper is pretty common for those type of applications. And then on top, there can be any kind of surface finish. This particular one here has an inic finish, so it's an electroless nickel, and then an immersion gold on top of that. But it also could be a tin plating, or a chemical tin, for example, depending on the value or the subsequent use of the part.
Gotcha. So then looking at our part that we've been building, now that it's been metallized, this one does not have the gold finish. It's more of just a copper finish. But this is our finished part. So just what is this thing? Well, it's actually a mobile device antenna, which is a huge area of application for LDS created molded interconnect devices, the telecommunications industry. Chances are you probably have an LDS antenna in your pocket right now, and that's actually pretty cool. So Stefan, talk about this application and why LDS is such a great fit for it. The smartphone industry really embraced the LDS technology, or the MIDs with LDS technology, very much so. And then there's a couple of reasons why it's so attractive for this particular industry. One of them is the human form factor. We try to put all these different functions into a phone these days, but our hands are not getting any bigger. So we have 5, 6, 7 or more antennas in these phones, and we need to keep them separated. So we have to use the space that's at hand, literally, no pun intended. So we started to wrap these antennas around all kinds of areas, and in order to do this efficiently, an MID or a molded interconnect device is really the only way to do that, because again, as we talked about it earlier, if we talk about a flex circuit, it starts its life as a 2D part, so it can't really be bent around what we call a double curved surface or sphere or something. So again, from the mechanical properties, an MID is a very attractive solution for these types of things. Now the other item, or the other function where an MID, or especially an LES-made MID, is very attractive for this industry is the point of the design freeze. Again, plastic parts can be molded ahead of time, and then the antenna can be still tweaked later. And we all know, the cell phone that you buy today is only good for a week, and then the new one's coming out. So again, this is a very fast-paced industry. So again, being able to move a design freeze out a little
go further is a very attractive proposition for this type of technology. So again, I think that's where LDS really fits the bill and makes it more attractive. It could even be into the extremes that, you know, one single plastic part could carry different types of antennas. Maybe one batch of antennas has, you know, CDMA antennas, and another one has GSM antennas, and it's still the same plastic part. So again, more flexibility in manufacturing can really make that happen too. So again, database manufacturing is really, it's the new world there. So.
Gotcha. Thanks for getting into that, Stefan. So another area of application that's huge for LDS is the automotive industry. And this part you can see here on the screen has a pretty cool story behind it. So Don, why don't you tell us that story?
Well, this is obviously a steering wheel. This is a human-machine interface here. It's what we call it. You know, it's basically the buttons on the steering wheel. And we all know the automotive industry can be a little risk-averse. And one thing I really like about this is this product started its life with with the same housing you see there, with a PC board hot stake to that housing, and then the circuitry was on the PC board. And in this case, not wanting to take a risk with changing the mold, they just simply recast that housing in an LDS grade plastic. Then they were able to take the PC board out of the equation and put the circuitry directly on the back of the housing. So you're removing that whole other assembly from the manufacturing process.
Gotcha, and I really like this one because it shows how you can just utilize the parts or the space that you're already using, and then just kind of save a lot of space and really increase efficiency in that regard. So moving on to this next application, Don, I'll keep you here since it's another automotive application, is this motorcycle handlebar. So talk to us what we're seeing here.
Again, it's a human-machine interface, and this gets back to kind of what Stefan says, is that our hands aren't getting any bigger, and yet if any of you rode a motorcycle years ago, there weren't a lot of functions involved in motorcycle riding. So, but now there's electronics in the motorcycles also, and so they've I think the application here was a 15 element switch on the handlebar itself. So basically, you've got to run 15 things with one thumb, and so you got to be really ergonomic about your design, and that's where LDS comes in. It allows you to do a 3D ergonomic design and put this directly on the structuring. If you can imagine, you know, bending a flex circuit or some sort of wiring harness around this small three-dimensional part would be very difficult. So LDS comes into play here very well, and this incorporates full 3D manufacturing. So this is done with a 3D pick-and-place machine, and the solder is put on in a 3D pick-and-place environment.
Gotcha, yeah. Again, Don, I just wanted to reemphasize what you said. I really love the 3D element of this part, and like you were mentioning, a lot of motorcycles, say you're watching Easy Rider, not a lot of functions on those motorcycle handlebars, but today there is. So
it really comes into play. I mean, LDS comes into play a lot in this human-machine interface because you can get ergonomics involved in your electrical design.
Awesome, thanks, Don. So another area of application for LDS is the medical industry. Here you can see this hearing aid application. So previously this part had a flex circuit in there, but now they're able to actually just, you know, utilize the ergonomic 3D shaping of that LDS allows and kind of create this part that actually carried 3 small microphones on it. So I wanted to talk to Stefan, talk about specifically for the medical industry, how the benefits of MIDs as far as weight carry out.
Yeah, so this is an interesting application here because, again, you can imagine that it's a hearing aid. So, you know, if somebody uses that device, they carry this, you know, in their ear, behind their ear, all day, every day. So every fraction of an ounce that we can shave off the weight of this part makes a huge difference. Now, again, functionality-wise, we want to be fully three-dimensional because there's multiple microphones going on this little carrier there, so we can have some more of a, you know, more natural sense of sound there. But at the same time, again, we want to make it simple and you know, comfortable to wear for the user of the device. So again, saving weight makes a big difference, and taking a rigid circuit board and doing away with this and using the plastic part that's in the item anyways, and add the circuitry to it, that really saves a lot of space here, a lot of weight in this part. And again, for a part like this that you carry all day every day, it makes all the difference in the world.
Gotcha. And then Don, I know that you have talked about the through-hole plating on this part. So talk a little bit about you know, plating vias when you're working with an LDS part.
One of the questions we get often about LDS is, can you do multi-layer? And because of the nature of it, you can't really do true multi-layer. But one of the ways you achieve this is by using front and back planes. So this part here has a molded through hole. So you mold, actually the through hole is part of the mold. the edges of the through hole are activated with the laser direct structuring process, and the edge, and it's plated through, so you get front to back connection on this part.
Gotcha. Thanks for explaining that, Don. Moving into the next application, which is actually my personal favorite LDS application, is this drill shield. So, Stefan, talk to us about what we're seeing here.
Yeah, so this is an interesting application that, again, it's a very good example for how to use the LDS technology in an area where it was really hard or virtually impossible to do this before. This is a plastic cover that has a circuit structure on it, and it's a security device that's used in ATMs or point-of-sale devices to detect intrusion of those devices. Now, of course, it's you see these really long, small lines, and you can imagine we initially talked about two-shot molding. If you try to mold or flow a liquid plastic in these very narrow, long channels, you can imagine this is not going to go on forever, and eventually the plastic will solidify and won't continue to go. Now, again, in the separation of molding and electrical circuitry through laser, now we don't have these limitations anymore. We can put any kind of circuitry on this plastic part. We can even change it all the time. So we can always stay ahead of the curve, and in the security industry, that's a big issue because we all want our money to be safe, don't we?
Definitely. I know I want my ATM to be secure. And then the other thing I really like about this application is, again, it really just shows how you can utilize the part and the space you already have and just throw some circuitry right on there with the LDS process. And then, so as Stefan talked about, these very fine traces that you can see on this part, with LDS, you're working obviously with a very small laser beam to create the circuitry. So kind of our standard for minimum trace and spacing requirements is 6 mils. Now, depending on the material, you can even get smaller than this, but generally, 6 mil traces with 6 mil spaces is very common for LDS MID applications. So this next application you're looking at is kind of this rugged RFID transponder. Don, talk to us a little bit about this application.
Well, as Shane pointed out, this is an RFID transponder. It's a good fit for LDS because it necessitates both long paths, both conductive and inductive paths within the part. So using the entire three-dimensional surface of your package to create these long, thin conductive lines on, it fits well with LDS. The other side of this is this can be used in a fairly harsh environment, either a manufacturing environment or harsh operating environments. And encasing it in a plastic and having it all part of a plastic case is advantageous in that situation.
Gotcha. Yeah, being able to withstand tolerances of the environment is huge, and I know they also use these on railroad cars as well. Another big application.
Yeah, some of these are actually autoclavable, so they go up to fairly high temperature rates.
Gotcha. Thanks, Don. And then our final application we're going to take a look at today is this barometric pressure sensor. And I know, Stefan, this is kind of like your favorite LDS application. So why?
Yeah, I love this application because it's a great representation of how to break the bonds of the two-dimensional world and really use a three-dimensional space very effectively. What we see here is a plastic packaging, a plastic housing of a chip, basically. You see a semiconductor inside, and then there's a pressure sensor on the right side of the part. But you probably noticed the absence of a lead frame in this part. So there's the semiconductor is directly wire bonded on the traces that are on the plastic housing that are created in the LDS technology. So again, we forego other parts. We reduce the parts count. We really start to become three-dimensional on this because the traces from the landing pads, from the semiconductor, from the wire bonding, go straight up the walls and up to the top where they become the pads for becoming an SMT component. So again, there's a great use of making a very small part. I believe these parts are used in watches. So again, everything has to be very small, very efficient, and it's a great way of really again breaking those boundaries and go beyond that and use the three-dimensional space.
And then Stefan, talk about the material this is made from and kind of the temperature constraints because of that.
Yeah, that's a good question, Jane. This material or this particular part is being used later on as in a mass production environment. So basically, they're sold as bulk parts and being used in any kind of soldering environment. So in order to accomplish this, of course, it's important that the plastic housing that's used for this particular part is compatible with most standard reflow soldering technologies, including, of course, lead-free applications. So I think this particular part is using an LCP material just in order to be very, very high temperature compatible. And also, of course, the molding quality of an LCP material would allow us to make a very small, very accurate part because we don't see any shrink in the mold there.
Gotcha. And then LCP is liquid crystal polymer, for those of you who were curious. So I see a lot of questions are coming in, and we're going to get to those in just a minute. So if you haven't heard your question answered, just hang tight. But I want to transition right here into kind of, we've taken a look at a lot of these MID applications, and we've talked a lot bit about their benefits. So to kind of sum it up, like, why would you want to consider using an MID? Well, as we mentioned, there's a lot less components involved. So the complexity of the design, of the overall design, and of the molding is going to be reduced. And beyond that, whether you're working in medical where it's huge, or even in automotive, you want lighter parts so that everything is more ergonomic and efficient. And then finally, that 3D workspace and the design versatility, using a 3D workspace allows. Again, this part on the screen, that motorcycle handlebar we looked at earlier, is really kind of a great example of just, using the 3D space you already have to throw your circuitry right on there. And then jumping off of that, why would you want to use LDS to create your MIDs? Well, as we mentioned, it's ideal for high-mix manufacturing environments. Whereas other MID manufacturing methods may only allow for large volume production, with LDS you can go from prototyping, just one or two parts, or you can go all the way through mass production of, as we saw earlier, mobile device antennas. Then, while the overall part is simpler, because you're using a very small laser beam to etch the wiring directly onto the plastic, you can create very complex circuitry, as we saw, say, for example, in the drill shield application. And then finally, it's really a cost-effective entry into the world of MIDs. And speaking of that, Steph, I'd like to bring you back in. So basically, if someone is kind of watching this presentation, they think LDS is really interesting, how could they get involved with working with this technology?
So yeah, again, as you saw, there's a lot of different things to the LDS technology, and it's a cultural change a little bit, because now we really have to kind of force mechanical and electrical designers around the same table and work on the same part at the same time rather than doing this sequentially. So if you're interested in LDS technology and you have a project that you think, hey, this is a perfect fit for this, and I want to really explore manufacturing opportunities, we can help you with the equipment and set you up if you want to start your own LDS manufacturing line. Or an alternative would be, if you're interested, we can find you a contract manufacturer that has all these technologies in place. And again, the best answer is call us, and we'll get you in contact with a service supplier that will fit your needs and your typical business model there. And again, the advantage on those service suppliers is, they of course have the equipment and the production technology, but they also have a lot of expertise in how to make three-dimensional parts. So if you're interested in going into this field, it may be wise to contact one of these companies that's shown here, plus many others that are really bringing a lot of design know-how to the party as well, and kind of get you started quickly.
Gotcha.
Now, if you're interested in just exploring the technology in a general sense, and you don't have a really fixed design that you're working with, but you're just looking at some technology demonstrators, we can help you with that too. We have a full application lab here at our location in Portland, Oregon. We have application engineering team here. So again, if you contact us, we'll help you to make your idea become reality. We'll get you parts and something that you can maybe bring up at your next management meeting and put on the conference room table, and maybe something that really, again, break the bonds of two dimensions now.
Awesome. Thanks, Stefan. So kind of that's the end of our presentation today. We really wanted to leave a lot of time for questions, so we'll get into those. So thanks for your attention, everyone, for stopping in today. We have the contact information up on the screen for Don, who's kind of our gateway to the MID LDS world here at LPKF. So if you do have any questions and you need to jump out, this is his information right there. But right now I see there's a lot of questions coming in, so I'm going to go ahead and start gathering those questions up so we can answer them. In the meantime, if you wouldn't mind, I'm going to launch a poll. Basically, what did you think of LDS? Maybe it's pretty interesting, but you're just curious at this time, or you think you might have an application, or even, you just like some more information maybe about temperature tolerances or materials, who knows. So again, I'm going to start collecting the questions. We're going to answer them here in a second, and if you could, launch the poll while I'm doing that. Thanks. All right, thanks everyone for taking part in that poll, and we're going to go ahead and dive into the questions now. So the first question I wanted to bring up is one I think we'll bring in Don for is Eric wanted to ask, so can the interconnection be formed between the top side and the bottom side, basically equivalent to vias in a PCB? Is the laser able to activate these holes? If yes, is the plated hole left in the final product, or do you have any way to cover or fill the hole? Don.
Okay, so starting from the beginning, there's two ways to do front-to-back interconnect with an LDS process. The most normal way, the most conventional way, the most common way to do it is to actually mold a through hole, and you mold this with kind of a conical entry point. So it's a cone going through the plastic, and you can have that going from both sides because you can structure from both sides. Then you have an angled surface to that hole, and you can activate that with the laser, and then that does plate through, so you get a full through connection with that. The other way you could do, typically on higher temperature thermoplastics, is you can actually drill through thinner areas on the substrate, and you get a very tight aspect ratio that way. So you can get a very small hole, and it does activate the sides also, so you can then plate that through. Can you overmold? Yes, you can overmold parts. I've seen paint on those very thin through holes, those drilled through holes. I've seen paint basically cover those up. So yeah, you can end up with a sealed through hole on these parts.
Gotcha. Thanks, Don. So our next question comes from Mike, who says, for early design where shear is not a concern, are there any advantages of LDS to a 3D printer for the plastic?
I think that's a great question there, and yes, the answer is 3D printer can definitely be used for LDS applications in two ways. There is from Stratasys, actually, from the 3D printer guys, there is an application where you can actually straight up print LDS parts directly off the 3D printer. So they print LDS grade PCABS material directly into those printers. So again, print a part 3D, throw it in the laser, put the circuitry on it, put it in the plating, and you have a part. So again, that's the kind of technology that we use here also for the prototyping. So if you are interested in us helping you with that, we are more than able and willing to do this with. Another alternative for 3D printing is we have a product called Proto Paint. This is a product that is designed to add LDS capability to any type of 3D printed part, because many 3D printers use proprietary plastic materials. Some of them, lower temperature, but most of them typically not LDS grade, like the Stratasys one. So in this case, you can print a 3D part and then spray paint an LDS layer on the outside of that, and then the part behaves just like an injection molded part that we described earlier in the webinar, where you can just create a circuitry on it and plate on it just like anything else. So again, 3D printing absolutely is definitely an option, and we have two different ways to do that.
Gotcha. Thanks, Stefan. And I know that both those ways are I've found in speaking with people are have a lot of favorable experiences. Stefan, I'll keep you here for this next question. Jim wanted to know, what are the circuitry limitations for LDS compared to a PCB or flex? He wants to know if a circuit on a PCB can be replicated on an MID created with LDS.
It technically could be. So an MID, and we talked about design limitations here earlier, what we see middle of the road design guidelines for MIDs is typically 6 mil traces in spaces, or 150 micron traces in spaces. So that's pretty common what you see in the board industry. Most rigid boards are in that area, or sometimes go down to 4 mil. Again, something that also can be done in MIDs. However, if you use an application that's currently a circuit board, replicating this on MID, it depends if this is the best way to go. MID really shines when we start to go beyond the two-dimensional world, break those bonds and go, again, circuitry up the wall, so to speak. Mm-hmm. That's when LDS really becomes attractive. But again, on tolerances and geometries, it's very much comparable to what a circuit board can be. There's no limitations on what type of circuitry you can put on there in terms of length or the density of the circuitry.
Gotcha. And then even speaking about taking a design from a PC board onto an MID, I know we looked at that automotive application earlier, where there's kind of used to be a PC board and they just transferred that design right onto the housing. So our next question comes from Column, who asks, do the metal ion loaded plastics have additional useful properties? For example, thermal or EMC?
Well, not usually, actually. I mean, usually it's somewhat, it does change the properties of the plastic somewhat. So we want to actually we typically minimize the amount of dopant that we put in any specific plastic. So when we qualify a certain thermoplastic, we're usually working with the minimal amount of dopant that we can add to get good plating and good adhesion still.
Gotcha. We have a lot of questions coming in, so I just want to say if you haven't heard yours yet, we'll get to it as soon as we can. But this next question comes from Warren, who asks a very shrewd question, which is, what's the comparative cost of the doped material to a conventional plastic?
Now, that's a very difficult question to answer for us. Again, as you probably heard in the beginning, we are the equipment manufacturers for the laser systems, and again, the plastic material is provided by a broad number of different resin manufacturers out there. So yeah, it's LDS grade material more expensive than its non-LDS grade alternative? Probably, I would say. How much is the premium price? I really won't be able to answer this, and it's probably a function of volume that you buy. If if you're buying small quantities, I'm sure the premium is a little higher than if you would buy very large quantity for consumer electronic applications. But I think it varies also from resin to resin. So if you're interested in a particular type of plastic resin, then we are more than happy to get you in contact with the resin manufacturers, and they can get you the pricing differences there.
Gotcha. And then you can see up here on the screen just some of the plastic suppliers that provide LDS grade plastics, everyone from Mitsubishi to BASF to RTP. So again, on our website, actually, you can see a full list of the materials that are available in LDS grade. We update that list all the time because there's always new materials being added to it. And then I can go ahead and follow up with you, Warren, and anyone else who wants. Just shoot me a message in the comments, and I can send you a link to that list of materials. So I'd like to get into the next question. Looks like John asked a couple questions about 3D printing. We covered that. Yes, you can use 3D printing for LDS. Also asked about the minimum trace width in space, which we just covered as well. Greg has an interesting question. He wants to know if LDS can be used with clear plastics.
Unfortunately not. That's I hate to say this, but no, it's not, because again we put a catalyst into the material, and I have not yet seen any plastic resins or LDS grade resins that are clear. The catalyst has it's almost like a color additive to the material, and of course it creates different colors. Most of the materials are black or dark gray. There's some materials that have blue tones or that are white materials. So again, there's some variations to it, but unfortunately there's no clear material.
Gotcha. Then I see a lot of people also asking about getting a copy of the presentation and or its slides, and we will follow up with you most likely tomorrow to get a copy of everything. Once we have a little editing process that we'll have to do and some processing with the presentation, but we'll make sure to get that to you. I have another question from Warren, who asks, what's the programming language for the laser? The circuit design itself is created in typically a step file. And oh yeah, thanks for bringing this on the screen here. That's one of our slides that we sometimes use for that. So here you see the circuitry on a plastic part. Again, it's a 3D step file in most cases, and then the circuitry itself is added as a zero height paint layer, so to speak, on that part. So we basically need two sets of data. We need the set of data for the part itself, for the topography of it, and we need the set of data for the circuitry, so we know where we want to run the laser beam and what height or what topography area we want to use that with. So again, step files is typically the most commonly used data format on this. I believe IGES files can be used as well. Gotcha. Thanks, Stefan. A question coming in from John, who says, what is the typical NRE and tooling costs?
Oh, that's very dependent on the part itself, but an NRE would, in a production environment, would take you into the mold also, but NRE on a part, maybe on a standard, on a fairly simple part, say like an antenna, you're probably into the $5,000 range, something like that, as far as software is concerned. Product development. The tool itself is fairly, or the tool for the mold is fairly expensive. But again, single shot molding is much less expensive than two-shot molding.
Gotcha. Yeah.
Yeah. Also, in terms of tooling cost for the lasers itself, we have a lot of possibilities there. We can use prototype tooling, which is basically an instant made putty material for individual parts if we do prototypes, or for mass production we can use fairly complicated fixtures that are really designed for very high throughput. Those toolings of course are more expensive than a simple prototyping tooling. So again, tooling cost varies very much with the type of use we want to get out of this tool, if it's a very high volume mass production consumer electronics part, or if it's an item that we're just going to make a handful of it for a specific prototyping application.
Gotcha. All right, so this next question comes from Jay, who asks, without mentioning any names, are you actively working with any military electronics OEMs on the LDS technology?
So yeah, the LDS technology is available for military applications, and I believe there's some military applications being used today. We have customers that are ITAR registered customers, and they can produce LDS parts for the military environment.
Gotcha. Thanks for being discreet with that, Stefan. So I have another question. This one comes from John. What is the surface mount compatibility with complex 3D structures such as the motorcycle handle? Does this need additional equipment?
Yeah. There's a few manufacturers that manufacture 3D SMT equipment. Now it's very specific to the 3D world. So it's and a lot of times it's custom made to an application. It's a little bit more complicated to set up and program than your typical SMT pick and place equipment, but generally works in the same way.
Gotcha. Thanks, Don. Okay, so here's a good question from Steve. He wants to know the entry cost for a prototyping LDS system.
Well, let's see. So next week, we're releasing our new prototyping lab system. So, I mean, you're generally into setting up a prototyping lab, and I can't talk too much about it this week, but we are at Productronica in Munich releasing an entire new system for prototyping, and you're generally into about $160,000 for the entire prototyping lab, and that takes you from the paint process that we went over briefly to a very simple prototyping plating system and a LDS laser.
Gotcha. And if any of you would like more information about the ProtoPaint product that we mentioned, go ahead and let us know, and we can get you more information about that.
Yeah, so maybe I can a few more notes on the prototyping process. Again, we're talking about again the laser for the circuit structuring, but also the plating itself. So we mentioned earlier in the webinar this is electroless plating, and electroless plating is not a too simple process in the mass production world. But again, one part of this prototyping package that we're about to introduce is really a very simple and easy to use plating method, something that can be used really in any type of lab environment, because that's really a bit of the missing link to make this technology really quickly available for any engineer. So again, this is a very big portion of making this very simple to use, not only the laser part but also the plating as well.
Gotcha. I have a question I missed from earlier. This comes from Mike, who says, what is the registration of the LDS laser?
I'll probably, I don't know exactly what you mean with registration. We're probably talking about tolerances or positioning accuracies or something. So maybe I can speak a little bit about the resolution of the lasers itself. The lasers are typically designed to the laser spot size is a combination of, being most effective in covering a large area and being small for high resolution. So most common systems use typically an 80 micron laser spot. However, we have fine focus options that can be as small as a 25 micron laser beam, so we can make very, very small circuit structures as well with those lasers, again with very high efficiencies.
Thanks, Evan. Question coming in from Tim. He wants to know, what is the typical current density of a finished part?
Now, the current density is a function of the thickness and the width of the plated part itself. As maybe Shane has a chance to go back to the cross section of the plating itself. We have, as we saw there's a typical thickness of electroless plating, which is not quite as thick as you see it with most standard 1 ounce or 35 micron circuit boards. So here the plating is typically quite thinner. So we see like a 5 micron copper here. It can be 8 or 12 micron copper. So as we start to get a little thicker, of course we can carry more current. However, one of the beautiful things is we typically have more real estate. So what we can't really achieve in thickness of metallization, we can make up in width of that, and that's again the additional real estate can help to compensate for this. But again, it's kind of a long-winded answer, but the current density, of course, is not quite as high as with a rigid circuit board with very thick copper plating on it, because we just deal with a thinner metal layer on that.
I'd like to add a nice little moment of levity to this situation. Someone out there apparently knows Stefan, because he's asking Stefan, should the Oregon Ducks football team be ranked #1?
That goes without saying.
We're big fans of the Ducks out here on the West Coast. Getting back into LDS, let me take a look at this question here. Greg wanted to know, what size are those formed metal seeds? So basically we looked at the molecular structure earlier of the metal atoms. How big are those? What are we looking at?
To be honest, I really don't know how big those metal parts are. But again, I think that varies a little bit. What we do here at LPKF is we work very closely with the plastics manufacturers in order for them to enable them to create an LDS grade metal. However, an LDS grade plastics. However, it is also important that different plastics have different characteristics, and we don't want to limit their capabilities all that much. So again, you probably see different fills or catalyst fills in different plastic materials. Again, a question is probably much better answered by the plastic resin manufacturers, such as RTP or BASF.
Gotcha. I have a good question coming here from Eric. He wants to know, so if we embed a small piece of metal, basically a small metal layer in the plastic during the molding process, are we able to use the laser to drill from the top and use that metal that they inserted as a stopping point?
Yeah, you can do that. It's very common to overmold a metal part within an MID, and then you can plate right up to that. You could also drill down to it. Also, I mean, I'd say it's more common to have a pin that comes out of the surface, and then the plating would you would just pattern up to that pin, and the plating would continue on to the tip of the pin. But you could also drill down to it or mold a via down to it.
Gotcha. Thanks, Don. All right, so we are slowing down a bit on questions, so I'm just going to check and see if there's anything we missed. If you have any more questions, feel free to get them in. We have 5 more minutes that we're going to be here answering questions. So let me look at our questions here really quick. All right, I have a question coming in from Jeff, who just submitted his question. He wants to know, how do you reflow? Can you use reflow components with the boards?
Yes, you can, if you choose the right plastic material. We've seen in one of the earlier slides, there's many different manufacturers of LDS grade plastic material out there. And some materials can be reflow soldered with a lead-free solder. Some others cannot. For example, PCABS material is a very common material that we see in antenna applications, but it's a very low temperature material, so it's not necessarily the first choice when it comes to solder on it. If you want to solder on a part, then the choice probably goes more towards a PA66T or a PPA material, a nylon-based plastic that has higher temperature and is lead-free solder compatible. And then again, if you want a really high temperature material, then probably you'd be talking about LCP or PEEK, and those type of LDS grades, they're compatible with any kind of solder process out there. Actually, interesting to know, there's new materials that are emerging right now. There's thermoset materials available that are they have solder temperature resistance like a regular circuit board material. So again, we're even moving to materials that are outside of the regular thermoplastics world, going into the thermoset material world.
Gotcha, Stefan. Yeah, and I know for Jeff, who asked that question, I just recently produced a video kind of going into the LDS materials a little bit, and I can actually send that link to you. It expands a little bit on what Stefan did, and then also I can refer you again to the materials list so you can kind of see what's available. Looks like we have a question from Nicholas, who asks, are there sources for data, for example, adhesion strength between plating and plastic between different LDS grade plastics?
I think I understand what you're asking for, and yes, we have when we qualify a plastic, we measure peel strength and plateability basically on the part, and when we do have characteristics for all the approved plastics, we have those characteristics available.
Thank you, John. Question coming in from John. This is a different John than who was asking before. He wants to know, has LDS been used on thermoformed parts? can you maybe do we need a little more information from John on that one?
Not that I know of. As far as I know, there's no thermoforming materials that are LDS compatible. Stefan brought up the epoxy basic the thermoset material, and that's probably the closest thing I could.
Okay.
Yeah.
John, if you wanted to maybe talk about this question a little bit more, we can probably follow up with you and kind of discover a little bit more about your question. I actually just wanted to thank Stefan and Don really quick because they're taking these questions really on a wing, really quickly, and kind of my fumbled delivery process. So thanks, guys. I think I've answered all the questions. Again, we have a couple more minutes. If you have any final questions, get them in. I'm just going to scan the questions, the questions for them really quick and see if there's anything we missed. So hang on just a second. Otherwise, we'll head out. Okay, so one more question from John. He wants to know, do we have a design guideline available for the LDS process?
Yes, I can. If you follow up with my link there or follow up with Shane, I can send that out to you. It's a nice and very useful document. Kind of gives you an overview of how you would design a part that can be made efficiently on an LDS machine.
The design guideline is also available for download on our website. So if you go to lpkfusa.com/MID in that area, you can also download this document. Again, it's a very useful document. Talks about how to design a part, what's efficient, what's not so efficient, how to use it, connection technologies, plating thicknesses, current density. So there's a whole slew of information that is very, very useful if you want to get into that. So.
Gotcha. And that was our final question of the day. So, John, we'll make sure to follow up with you specifically with that LDS guideline. But again, thanks everyone. We have a ton of people stick throughout the whole questions area, questions time. So, thanks again for stopping in today to the presentation. I wanted to thank our panel, Stefan and Don. Thanks, guys, for joining us.
Thanks, Shane.
Thank you, Shane.
All right, and once more, thanks everyone for watching, and go Ducks.